in the middle, or the voltage of the rod on the side, for example. So let's say there's a uniform charged rod, negative L over 2 to L over 2. So I could take if I want to get a general equation for this and general equation for that, I could get the equation that we have from electric field and take the negative integral of that, you see. So if you go back to the electrical field, we have an equation for the electric field of a rod, KQ over D L squared over, was it L squared over 4 plus D squared to the 3 halves, was it? 3 halves as D infinity. We can always, I believe it's 1/2. Okay, sure. This is the general equation for the electrical field of a rod in the middle. Okay. If I want to get a voltage equation for voltage for the rod in the middle, then I would just take the negative integral of that. Negative integral E. Well, let's call this distance R, because it gets confusing. So let's say negative integral E dr. So then I would take the integral of that. Ew, that's kind of nasty. So it's not something that you would probably do. KQ over integral R L squared over 4 plus R squared half from R to infinity. So basically I would say from some R to infinity, that gives me the the voltage. Oh, that's a nasty integral. Yeah, we'll probably have to go put it into the integral function. So therefore, that's not advantageous to us to do it that way. Then the better approach would be to say, well, let me calculate the voltage for the rod just like I would the voltage of an electric field, right? Take a piece from here. dq, right? But with voltage, you don't have to use symmetry. You can say, okay, the voltage created by that dq is K dq over R. So then we have dV is equal to K dq over, and then this distance is X, right? So then you have X squared plus D squared to the 1/2 power. Right, so the voltage created by dq at that point, K dq over X squared plus D squared to the 1/2. And then that's it. Just integrate from negative L over 2 to L over 2. And that gives you the equation already. So then dq is going to be lambda dx. And then lambda is going to be Q, it's going to come out of the integral Q over L, integral dx, X squared plus D squared to the 1/2. And I'm going to integrate 0 to L over 2. Then I'm going to double it. 2kq over L dx. Even this wasn't that easy of an integral, but it's easier than doing this. In other words, if I know the equation for the electric field, I can say I can negative integrate it or just do it by piecewise integration. This is piecewise integration, taking pieces of the rod and integrating the voltage that each of those pieces is creating. You see? So then let me go to online integral and integrate that. Online integral. So 1 divided by x squared plus d squared to the power 0.5. Zero to L over 2. Inverse hyperbolic L over 2D. So the integral portion came out to be that, sine inverse hyperbolic L over 2D, and then you got the 2kq over L. Yeah, so it's kind of a weird looking equation. But how could we check to see if this answer is true? Now I can go the other way. I can take negative the derivative of this, and it should give me our famous equation for the electrical field, right? If I take the derivative of it, I prefer writing R when I'm taking derivative. So then E is equal to negative dV dr. So you see how you could go either way. If you have the equation for E, negative integral of it, but then when you're taking integral, it's a little bit harder because you're doing it from R to infinity. That's why it's easier to calculate voltage and take negative derivative of it to check if you get this answer, you see. And plus voltage is easier to calculate usually. So if you take negative the derivative of this, you get negative 2kq over L. What's the derivative of inverse sine hyperbolic? Wow, who's going to remember that? Derivative of sine or arc sine hyperbolic. Is that how they write arc sine hyperbolic? Okay, so the function is sine arc sine hyperbolic. Oh, this is the way they write it, huh? Sine hyperbolic to the minus 1. So if I take the derivative of this, okay, so remember I'm taking negative the derivative of it. So negative 2kq over L, 1 over square root of this thing. This thing is L over 2r squared plus 1, but then times the derivative of the inside, right? I'm taking the derivative of this with respect to r. So then what would be the derivative of this guy? Negative L over 2r squared. Yeah, 2r, negative, yeah, negative L over 2r squared. Okay, now when I simplify this, I'm supposed to be getting this one. if I did it right. So if I take the general voltage equation and take the derivative of it, negative derivative of it, and I should get that one. Oh, let's see, oh, I think I am. Oh my gosh. I think I am. Yay! Ooh, negative cancel. See, we needed an exciting moment here. We needed a revelatory moment. L cancels. 2 cancels. Okay. And now, if I'm trying to make this look like that, what do I do? 2 squared is a 4. I could cross multiply, take the r out. So I'll write it as what? KQ. There's an r squared here, right? Over r squared. And then this one will be 1 over, God, I can't believe this. This is great. L squared over 4 plus the r squared like that. And then take it out of the radical as a 1 over r. You see? So take this r squared and put it here and have it over the bottom, and then take it out of the radical as 1 over r. And then this one cancels this one. Yes. Wow. KQ over R. L squared over 4 plus R squared. Beautiful. Okay, so that would be then, therefore, the general equation for the voltage. Even though voltage is easier to calculate, you don't have to worry about directions, but the answer the general answer came up kind of weird looking. But then when you take negative derivative of it, you did get the electrical field. So that's cool. Okay, how about off to the side? What's the general answer for the voltage? Do we have a general answer for the electrical field off to the side? When we did it back then?
So it was the Coulomb constant times big Q over D times quantity L plus B.
Quantity, D times quantity.
L plus B.
Oh, that was it? Oh. Oh yeah, very easy looking. So the voltage should also be pretty easy looking. So if one wanted to calculate the voltage, you just take a little piece. Then you say the voltage created by that piece is K dQ over X. In this case, it's very similar to the electrical field, except, you're just not doing direction. But the electrical field was easy on the side anyway, because you didn't have to worry about cancellations. So then you just have here, what was this is L over 2. And then this is D. And then this distance was what? Your R. So then remember how we found R? We said R was, let's see here, L over 2 plus D. We said was equal to X plus R. So then R is L over 2 plus D minus X. Okay, so except we just don't have the square here in this case, you see. So then we say the dq is equal to lambda dx. And then integrate it from negative L over 2 to L over 2. Remember this one, you can't double it. Okay, so then the voltage comes out KQ over L integral negative L over 2 to L over 2 dx over L over 2 plus d minus x. Oh, this is going to be a ln function, right? ln. Voltage KQ over L. It's going to be a negative ln function, negative ln of L over 2 plus d minus x from negative L over 2 to L over 2. Right? Or I could reverse the direction, the integral like this, L over 2 to negative L over 2, and then put this here, so it'll be voltage is KQ over L, ln of, and put negative L over 2 here, so L over 2 plus D minus negative L over 2 minus ln of L over 2 plus D minus L over 2. Okay, so then this cancels. So then you have KQ over L, ln of, it's going to be just L plus D minus ln of what? D. So that's the general equation for the voltage on the side of a non-uniform charge. Okay. The general equation for the voltage and the general equation. So now we have the general equation for both. If I take negative the derivative of that, that should give me the electric field equation. It's interesting. The electric field equation looks easier than this one. Okay. So now if I take negative the derivative of that, so let's change it to an R again. So negative dV dr, because I don't want to do negative dV dd, you know, that's why I change it to R. So then what would negative KQ over L, what would be the derivative of that? That's just easy, right? 1 over L plus R minus 1 over R. Right, so minus 1 over this, minus 1 over this. Then you got the other minus because of the negative dV dr. And then this switches the sign, right? And then you can combine these. What should happen? Well, the final answer should be giving you the equation that we have for the electric field, this one. So KQ over L, negative R plus L plus R over R times L plus R. Right, so I'm combining this and then cross multiplying and adding them, and then you have what? Negative R cancels, nice. And the L cancels the L, nice. There you go. It's surprising, it always comes out. KQ over R, L plus R. Okay, now let's get numerical answers just so we can see what we're dealing with here. So if your charge is 10 nanocoulombs and the length of the rod 1 meter, what's the voltage, let's say 1 meter away, for R is 1 meter. So on the side, so if you have a rod like this, so 1 meter, and then it would be something like this, 1 meter away. Same distance as the length of the rod. So then we would just do this one, voltage, 9, and then the 10. The nano will cancel the 10 to the 9th, and then divide it by 1. So 9, 10, 1, and then ln of 1 plus 1, right? So that's going to be ln of 2 minus ln of 1. Oh, okay, that's easy. So just this cancels. Okay, then you just have 90 times ln of 2. (62.38 volts). Okay, how about 1 meter this way from the middle, which would be somewhere here. So 62.38 volts, and then 1 meter. So what was the general equation for the middle? Oh, it was the sine hyperbolic equation, right? Two, 9, then Q is 10, or the length is 1, sine inverse hyperbolic, then you have 1 over 2, 1, so that's just 1 over 2, which is 0.5. Oh, iPhone has a sine inverse hyperbolic. Cool. Who would think? You see that? Sine inverse hyperbolic. So let's see here. So we do 0.5 sine hyperbolic inverse. Okay. Times, and then 2k q over L. That's it. So 1880. So 86.618 volts. Okay, let's check that with the simulation, and then we'll call it the day for today. So let's check these two answers. So it's a 10 nanocoulomb charge. Where is my trustworthy simulation? So we're checking voltage here. So 1 meter away. What did we get? 62.38, right? Ah, yeah, we're pretty close. Nice. 62.38. And remember, I could do this pen, then it shows me all the places where it's 62.38. What kind of an equation does that look like to you guys? Does that look like a circle? It looks more like an ellipse, right? Because this distance from here to here, the distance from here to here, 150. Yeah, it's an ellipse. It looks like the path of the Earth takes around the sun, right? So, yeah, it's not circular. Try finding the equation of that line. Wow. Okay, so then 1 meter from the other one would be what? Is this the center? So 1 meter would be right there. What did we get? 86. Okay, we're in the ballpark. Probably I didn't place these really nicely. Yeah, I'm a little bit off, but I'm close. Yeah. See, 86.618. Okay, and then we can also click that one. So notice that the voltage drops 1 meter this way. The voltage drops quicker than the 1 meter this way, because you're kind of farther away from the left charges, right? So the voltage drops quicker this way. If we draw, you can kind of see generally what the voltage equipotential surfaces look like. It's nice. Okay, cool.